Welcome back everyone. We will continue with more definitions of representation theory of Lie algebras. So, in this lecture I will define all important terminologies that will be used throughout this course like submodules, irreducible modules, indecomposable modules and so on. So, let us begin with uh, basic definitions. So, now let us define what is called g-submodule. So, let V be a G module of the Lie algebra G. So, and W be a subspace of V. So, this is subspace which is a C vector space. So, then we call submodule. So, G submodule. So, we say W is a G submodule if whenever we take element x in G and vector v in W, then if we look at the action of x on V, so that should be inside W for all x in G and v in W. So, that means if we take the action of G restricted to W, okay, then W become invariant under this action. Okay. So, W becomes G invariant with respect to the action of G. So, now it is easy to see that if we define this following map, okay, for example, let us say pi is the given representation corresponding to the G module V. So, then we have the map from G to GL of V. So, now what we can do, we can actually define this new map pi tilde from G to GL of W by the following. Let us say x goes to xv is the map that is given by pi. So, then this pi tilde is nothing but x goes to xv restricted to W. So, that is the map that we are talking about. And it is easy to see that if W is a submodule, then this pi tilde that is given by x goes to xv restricted to W gives you representation of G that is acting on W. Okay. So, sometimes we also call this W as a sub representation, okay, sub representation of capital V. So, like I said in the earlier class, representation and modules will be used like interchangeably throughout this course. So, now we define what is called indecomposable modules. Okay. So, here is the definition of indecomposable G modules. So, let us say V is a given G module. Okay. So, let us first define what is called decomposable, then it becomes easy to define what is indecomposable. So, decomposable means, so given a representation, let us say V is G module. So, then V is said to be decomposable, V is said to be decomposable if there exist two sub representations or submodules. If there exists W1 and W2, both of them are G submodules of capital V, such that this V is nothing but W1 direct sum W2. Okay. So, in that case we say that V is decomposable G module. And what is indecomposable G module? If V cannot be written as W1 direct sum W2 for any non-trivial G submodules, then we call it V is indecomposable. So, suppose V is written as W1 direct sum W2 for some submodules W1 and W2, then that should imply that either W1 is 0 or W2 is 0. So, if V satisfies this condition, then we call V is indecomposable. So, V is indecomposable if V satisfies this condition. Okay. And one can prove that any finite dimensional representation must be direct sum of indecomposable representation. Okay, that one can do it by induction on the dimension. Okay, let us prove that proportion, because this proportion is very important. Okay, so here is the proportion. So what it says, any finite dimensional G module is a direct sum of indecomposable representations G mod. Okay, how one can prove this? We will use induction. Okay, if to begin with V is trivial or 0, then we do not need to worry about it. So, if V is actually let us say dimension more than 1, okay, if dimension of V is either 0 or 1, then there is nothing to prove, because they are indecomposable modules. If the dimension is more than 1, if it is actually already to begin with indecomposable, then again nothing to prove, because it is trivially decomposed into indecomposable, and V is indecomposable, then V equal to V. So, there is nothing to prove. So, one can assume that dimension V is more than 1 and V is decomposable. So, in that case, V can be written as W1 direct sum W2, and both W1 and W2 both are non-zero modules. So, that implies that the dimension of W1 must be strictly less than the dimension of V, and the dimension of W2 must be strictly less than dimension of V. If it is equal, then that would imply that the other one is 0. Okay. So, that means we can use induction on the dimension and then assume that W1 and W2 both of them are direct sum of some indecomposable submodules. Okay. So, by induction one can assume that both W1 and W2 are direct sum of indecomposable G submodules. Submodules of W1, W2 will be submodule of V. So, that would imply that by adding them together, we can see that V is the direct sum of indecomposable G submodules of V. Okay. So, this completes the proof of this proportion, which tells us that any finite dimensional G module must be actually direct sum of indecomposable G modules. So, now this actually proposes many questions. So, the very first question is, so can we classify all the indecomposable modules? And even if we classify, okay, how one can write given finite dimensional module as direct sum of indecomposable modules. So, we should actually propose an algorithm. So, this result is actually very similar to prime factorization for integers. Okay. So, given any integer, one can write that integer as product of primes, okay, up to unit. So, then it is not only like theoretically one can prove that prime factorization exists, but practically speaking, given integer, how one can actually write that integer as product of primes, so that is a big question. So, similar to that, so this will be actually somewhat difficult task to say. So, given representation, how one can write it as a direct sum of indecomposable representation. So, there are two important problems here. Okay. The problem 1. So, if we classify all indecomposable G representation, that actually tells us that how to classify any finite dimensional representation, because any finite dimensional representation is a direct sum of indecomposable representation. Okay. So, the first problem is classify all indecomposable, of course, finite dimensional G modules. So, because we are only interested in finite dimensional representations of G. So, what will be the problem 2? So, given finite dimensional representation of G, how one can decompose this into indecomposable representation. So, theoretically, we know that any given finite dimensional representation can be written as direct sum of indecomposable, and that proof is very simple as it is in the integers. Okay. Any integer can be written as product of primes. So, very similar to that, one can prove that any finite dimensional G module is a direct sum of indecomposable G module. So, this is just a very simple proof. But given finite dimensional representation, how one can decompose, whether there is any algorithm to do this and so on, that is actually most difficult question. So, we will see later that okay, for at least SLN. Okay. So, because SLN being simple Lie algebra, okay, for SLN using this Weil's theorem, we can see that indecomposable modules will correspond to irreducible modules. So, indecomposable will be same as irreducible. Okay. So, this is what actually Cartan killing theory tells us. So, if we actually, it is easy to see, I will leave it as exercise. So, it is a very simple exercise for any Lie algebra G. If we take irreducible module, okay, finite dimensional irreducible module, G module. So, then suppose V is finite dimensional irreducible module, then V must be indecomposable module. Because irreducible by definition, the only submodules of V will be trivial and itself, and if V is decomposable, then it will be decomposed into W1 direct sum W2. Both W1 W2 will be non-trivial representations. Okay, that would actually lead to the contradiction. So, that is why all the irreducible modules must be indecomposable, but the converse need not be true in general. But if we take simple Lie algebra or semi-simple Lie algebra, then this is true. All indecomposable modules will correspond to irreducible modules. So, at least using the Weil's theorem, one can see that for SLN, like classifying indecomposable finite dimensional G module will be equivalent to classifying all the irreducible modules. Using the highest weight theory, one can actually classify all the irreducible SLN modules. So, that is what we will be doing later in this course. Okay. So, our ultimate goal, so this is the ultimate goal, to classify all finite dimensional irreducible SLN modules. Of course, once we understand the representation theory of SLN, then there is a close relationship with this representation theory and representation theory of GLN. So, using that close relationship, we can also understand the representation theory of GLN. So, now let us move on. I guess I defined submodule and then indecomposable module. So, we will now define irreducible module. Anyway, I used the notion already, but irreducible module means it is a G module and that has 0 and V itself as only submodules. Okay. V is said to be irreducible G module if 0 and V are the only G submodules of V. Okay. So, the notion of irreducible modules, they are very important. That is because indecomposable modules are same as irreducible modules, and whilst complete reducibility tells us that any finite dimensional representation of SLN can be written as direct sum of irreducible modules. So, that will actually reduce our problem of classifying finite dimensional representation of SLN to classifying all irreducible modules. So, first we will do this for SL2 and then later for SL3, and then after that we will generalize everything to SLN. Okay. So, now we have this notion. So, once we have introduced this notion, we can actually make some actually trivial remarks. So, for example, if V is irreducible G module, so then we can pick a vector and then look at the smallest possible submodule that contains V. So, if you pick a non-zero vector, then capital V will be the smallest module. Okay. So, smallest with respect to the inclusion. So, let us start with okay, this is the observation. Okay. So, let V be an irreducible G module. So, then one can pick a vector capital V in V. So, we can take any vector, okay, for any vector V in capital V. If we look at this smallest module that actually containing V, okay, this is the intersection of all G submodules containing V. So, this is what the submodule generated by V. Okay, this is the submodule, okay, G submodule generated by V. So, one can easily see that because V is being irreducible, there are no other submodules other than 0 and itself. So, because V we picked as non-zero element in capital V, so that would imply that the submodule generated by V, that is the smallest module that containing V, must be exactly capital V. So, this is very important observation and this will be used again and again in this course. Okay, similar to this, we can also talk about a submodule generated by any subset. So, let us define that. So, let V be a G module, and we can actually take any subset S of V. Okay, this is just a subset. So, then we can actually define what is called submodule generated by the subset capital S. So, usually we denote it by this notation. So, what is this? So, this is by definition g-Submodule generated by capital S. So, what is this? This is actually the smallest module that contains capital S. So, it is easy to see that intersection of G module will be again G module. So, you can take any arbitrary intersection, that does not matter. So, if we take all possible modules that containing S, that set must be non-empty because capital V is there. So, in particularly what we can do, we can take intersection of all submodules W, W contains S and W is a g-Submodule of capital V, then this intersection will be actually valid inside any module capital V, and this intersection contains capital S, okay, and one can easily see that this is the smallest submodule that contains V, and this is defined to be the submodule generated by capital S. Okay. So, what is this property? Let me write it as a proportion. If W contains S and W is a g-Submodule of capital V, then definitely W contains the submodule generated by capital S. Okay. So, to explicitly write down what will be the spanning set of capital S, we need the notion of universal Olympic algebra. So, actually without telling that, one can actually work inside GL of V and then try to get the spanning set for this the submodule generated by S. So, let us see how one can actually get that. So, this is actually very important thing. Okay. So, let us see. So, let us start with V being a G module. So, V is G module and S is a subset. Okay, let us say this V G module is given by this representation pi. So, which is a map from G to GL of V. Okay. So, given x, we have this pi of x, which actually we denoted by xv. Okay. So, note that inside GL of V, we also have a matrix multiplication, or we have the composition of maps. Okay. So, this GL of V is nothing but endomorphism of V. Okay. So, in endomorphism of V, that is indeed an associative algebra. So, we also have composition of maps that gives you multiplication there. So, using that, we can actually make sense of composition of two elements that actually comes from G. Okay. So, if we take x in G, y in G, then we can talk about xv composition yv inside endomorphism of V. That makes sense. That means we can actually allow the product xy inside endomorphism of V. That makes sense. So, now if we take this g-Submodule generated by S, the g-Submodule generated by capital S. So, how it is going to look like? Let us see. Suppose if I take a vector capital S in V and x in G, then we can actually look at what is xv. So, xv is nothing but xv applied on V. Okay. So, this must be inside your submodule generated by S. Okay. So, not only that, if we take another y in G, okay, so then I can also compose y x v. So, that is y v x v, that is also inside your submodule generated by S. So, that means it is actually makes sense to denote this by just symbolically xyv. Okay, even though the multiplication yx doesn't make sense inside G, but yx acting on V makes sense inside capital V. So, one can take the composition of yv and xv. So, that is what we mean by this symbol. For example, we say x square v by, we take xv square acting on V. So, xv square makes sense inside endomorphism of V. So, that is what we mean by this. So, this is the notation we will be using. Okay. So, this is the notation. So, for example, xv yv acting on V is just will be denoted by x by of V. Okay. Now, using this one can easily see that. So, this subspace, one can start with the subspace span by S, okay, and then take all the elements of G and then keep repeatedly acting on that. So, then by taking the span of that, we will be getting the G submodule. So, basically what will be this G submodule generated by S? So, we can take span of, okay. So, we can pick a vector and then repeatedly apply element of G, okay. So, we can take xi1 etc xir and then we can apply it on V, and then this xi1 etc xir we can pick it from G, and then this vector we can pick it from S. And if we take span of all this, so this is going to be vector subspace first of all. So, this is a vector subspace of capital V by definition. Okay. So, now we claim that this is indeed smallest module containing S. Okay. So, first of all, S is there by allowing, okay, this R we can actually take it to be greater than or equal to 0. When R is 0, we just treat this xi1 etc xir of V to be just V. Okay. This is like a empty thing applied on V, which is gives back V. Okay. So, this is the notation. So, now using this we can see that the right hand side is indeed G module. So, how one can verify this? We can pick x in G and then we can pick any element in the right hand side, which will be a linear combination of elements of this form. So, because of that we can just pick one of this element from the spanning set. Okay. So, now if you apply x on this, then what we get is just x, xi1 etc xir, which is applied on V, okay, which is also of the same form like this. Okay. So, this form is and this form both are same, and or we are allowed to take any or greater than or equal to 0. So, that means, so this is going to be again inside this collection, call this collection A. Okay. So, that is going, so that means the right hand side is indeed closed under the action of G. So, this is all just a symbolic computation, okay. But what one should remember, what is the meaning of xi1 etc xir applied on V. So, this means you keep applying the maps xi1 V composed, xi2 V composed etc xir V applied on small v. So, that is what this map means. Okay. So, now if you use this, then you can easily see that the right hand side is closed under the G action and S is contained in there. So, that means the right hand side contains the submodule generated by S. Now, if we take any vector V in capital S and then if you keep applying the elements of G, so then those elements after that applying elements of G must be lying inside the submodule generated by S. So, it is easy to see that. So, this submodule generated by S contains the right hand side. So, that implies right hand side is the smallest module generated by S. Okay. So, this is actually kind of theoretically speaking very rough spanning set that we are getting it for submodule generated by S. So, later we will see that after introducing universal and helping algebra, that how to actually choose some spanning set much more cleverly. Okay. So, I will actually end with another small observation. So, if we work with the general G module, so if we take some element from the derived algebra, so then one can easily see that the trace of that element, okay, that will must be 0. Okay. So, here is the important observation. You start with V being a G module. Now, take X from the derived algebra GG. Note that the derived algebra is span of the brackets YZ, where Y and Z both comes from G. So, now what we want to do, we want to understand what is the trace of this XV. So, the trace of XV going to be, so X will be the sum of finite sum of these elements from I range from 1 to K. So, then the trace of this XV is going to be trace of these elements I range from 1 to K, but note that both yi zi leaves this V invariant. So, that means this bracket yi zi V is going to be exactly equal to yi V times zi V minus zi V times yi V. So, that means the trace of this element must be 0. So, that will force that the trace of x v is 0. So, this is indeed important observation. For example, if we take W to be any submodule, then the trace of this bracket YZ, okay, also will be 0 when you calculate its action restricted to W. Okay. So, these informations will be used repeatedly to actually classify, for example, irreducible representations of SL2 and so on. Okay, we will stop here. I will continue with some more examples of representations in the next class. Thank you very much.